This physics problem has been blowing up the internet. In fact, in a recent post on X, this physics problem gained 6 million views. And then the next day, it gained another 4 million views. For over 10 million views in 2 days. But that's not all. When it made it to YouTube, it gained another 2 million views. And the answers are all over the place. We've got people saying that scales can't read. We've got people saying people can't read scales. We've got other people angry at academics. And lastly, nobody's done any real experiments. Commenters on Wrath of Math's video point out that we really do need a demonstration of this. And that's where I come in, because my channel is literally about demonstrating physics. So let's get into it. Here's our experimental setup. It's pretty similar to the initial problem, except I need to use 2.5 pounds instead of 100 Newton weights. To stay close to the original problem, let's do a quick conversion to Newtons. Okay, cool. So we have our problem set up now, and we can actually write out the exact same statement for the problem we're going to solve with the demonstration. The question is, does the scale read 11 newtons, 22 newtons, or 0 newtons? To set this problem up, we're going to use these two 2.5 pound weights, we're going to use a bunch of thread, and then we're going to use this force gauge that you see here. I'm going to tie the thread together and then double it up on the weights and connecting to the force gauge, because when I tried this without doing that, it just broke and everything fell to the ground. Once the strings are tied and the bottom of the force gauge is attached, we're ready for our experiment. Before we start the experiment, we should make sure that it's actually working and registering forces. Alright, we're about there. The last thing we need to do is measure this weight and make sure that it's actually clocking in at the weight that we expect in newtons. That's hard to read, so let me flip it over. Each decrement or line on the outer circle represents 1/4 of a newton. So you can see here that we've got 10 3/4 of a newton by the scale. Now this isn't that surprising because these weights are about 20 years old and probably weren't cast with such high precision. Alright, time for the experiment. Here it is. We've got the setup just like in the picture. And the result is 0. Wait a minute, that doesn't seem right. Let me wiggle this around and see what happens. Huh, do you think that's the right result? Did you notice earlier when I showed you the force gauge that both ends move in unison? Well, that's a problem for our experiment. Here's an approximate view of the force gauge. You can see the spring surrounding the rod that connects both ends. The gauge works based on Hooke's law, which says that force is proportional to length traveled for a linear spring. And so the force is equal to some constant times x, where x is the length traveled. Returning to our force gauge, we see that as we push or pull on either end, the spring will move relative to the outer body and measure what the force is. The key point is that it's relative to the body of the force gauge, which means we need to make our connection not to the bottom of the force gauge, but to the force gauge body. And we're going to do that using some duct tape. Here's experiment number 2, where we've connected to the body and not to the bottom of the force gauge. And the reading on the force gauge is 10 newtons. Nice. So you may be wondering, why is 10 newtons nice if it's supposed to be measuring a little over 11 newtons? Well, the reason being is because there's experimental error. And as you can see here, as I kind of pull and I kind of push or let go of the force gauge, we're hovering anywhere between 9 to 12 newtons on the force gauge. And so coming in at 10 newtons is actually well within the experimental range. Let me draw you a quick bar graph of each of the possible solutions. So we had 0, we had 11 newtons, and then we had 22 newtons. And so this is represented by blue, purple, and red. Due to our experimental error, we can add some error bars on each of these bar graphs. Since each of the solutions is far enough apart, none of the uncertainty ranges overlap. And therefore, finding a solution within our uncertainty range lets us conclude that the answer is indeed 11 newtons. And using our results scaled back to the original problem, we conclude 100 newtons. Now don't feel bad if you didn't get this problem right. This is actually a college level physics problem at UCLA. So, did the result make sense to you? Let me know in the comments. If you enjoyed the video, make sure to give it a like. And if you enjoy STEM related content, make sure to subscribe. And if you're ready for another video, I think you might enjoy this video on pendulum motion.